Hey folks, Professor Finn here, and today we're going to be looking at chemistry part 2. So when I first started teaching chemistry many years ago, I just absolutely did not understand this stuff. Like, I was one of those professors, just read it from the book and suck it up, buttercup, you're going to get it that way. Time has changed. Time has changed. I understand the subject a hell of a lot better than I ever did. So I figured that I would go ahead and I would re-record the hydrocarbon lecture and then do some of that other stuff later, because I think it's really important that if you really want to master this, you really want to play with it, and hopefully by playing with it, you absolutely get a better grasp of it. This is an approach that you can actually use. So let's go ahead and dive into the PowerPoint, and I am going to scribble on this thing. As we go, I will be dragging a whiteboard to and from the screen in order to illustrate other things as we go. And by all means, folks, during one of the Fridays with Finn sessions, when I boot those back up in August, absolutely, if you have questions about this, get with me so I can demonstrate, because this is one of those topics, unless you have questions, it's really, really dry and people don't really care about it. So, organic compounds are divided into different classes of compounds based on the elements that are present in the functional groups that may be present. I found this chart on, what was it, Biology Corner? Yeah, Biology Corner, to give you an idea of the number of compounds out there. And in the course, whether it's a chemistry course at a mortuary school or here in Miami, we used to teach this FSC 1105, thanatochemistry, you're actually going to see that we're going to talk an awful lot about some of these compounds. Like, if we go through, we're definitely going to talk about carbohydrates, proteins. We're going to be talking about how enzymes react. We're going to be talking about a lot of the stuff in this course, especially later on. So the first thing we're going to start with is the simplest compound that we have, which is a hydrocarbon. Okay? The name implies it. You have hydrogen, you have carbon, that's it. An organic compound containing only carbon and hydrogen. There are other subdivisions. We can talk about the ways that they're bonded. We can talk about the molecules that they form. So this is where people start to get lost. First thing, keep this simple. Acyclic means chain. Aliphatic means chain. All your hydrocarbons are going to do something like that. So if you see aliphatic, all that means is the word chain. And if while you're studying, you see the word aliphatic in your notes, write chain until your brain recognizes that as a chain. It's a very important thing. The next thing is aromatic. Now, at this point, as we're studying this, aromatic equals circle. I know there's going to be some chemistry people out there right now that are losing their minds. Absolutely, drop your hot trash in the comments. Tell me what an idiot I am. The more you yell at me, the more I feel happy, because I'm just one of those weird type of people. But think circle. Okay, think circle. Cyclic absolutely will imply whatever. But aromatic means circle, and right now that's all you have to care about. That if you see something like this, that does not equal a chain. So this would be aromatic, this would be aliphatic. This can also be known as closed chain. We're going to see that coming up here in the lecture. Closed chain. Okay? Next we have the types of bonds that are present. So here's the first thing you start doing on every piece of scratch paper every time you study, is you write this on the right-hand side as you're practicing chemistry, and then on scratch paper going forward. A-N-E, E-N-E, Y-N-E, and then I'm just going to write SC, but that stands for side chain. And while you're learning, I strongly encourage you write the word side chain. Okay? Now, I tell my students this. I'm not joking. Every piece of scratch paper, every one of them. It doesn't matter if you're taking small business management, if you're in your funeral service counseling or thanatology class, if you are permitted scrap paper, when you sit down, the first thing you should write, 1, 2, 3, YL, ein, ein, side chain. especially if your professor is expecting you to be able to draw these things out and identify them. Okay, if your professor's not going to do that, then why are you even listening to this lecture? 1,2,3YL sidechain. Not the only thing you're going to be writing down for this course, but that's where you're going to start because that's the way this subject, why this book brings it up. And for those of you who don't know which book I'm using Chemistry for Funeral Service by Professional Trade Schools. There are much better books on the market. There are much better books on the market by far. I encourage you, go out there, take a look and see what's out there. I have found this to be the smallest book that gives you what you need to know, but man, if someone doesn't explain it to you, good luck with that. Now, if you want a more true-to-life textbook, okay? If you want a more true-to-life textbook for the study of chemistry. And in this textbook, folks, okay, in this textbook, they do not spend a lot of time, if any time, talking about how to name molecules. So this is the danger of different texts doing different things. But an absolutely phenomenal textbook for the study of chemistry is Turning Art into Science by Dr. Damon de la Cruz and Dr. Robert Holmes. Now, this is the same Dr. Damon, Dr. de la Cruz that does the videos on YouTube. The man is a brilliant chemist, okay? The man knows his stuff. This is a great book. If Damon corrects me, you obey what Damon says. It's as simple as that. But in that textbook, they do not go heavy into naming hydrocarbons. I find if you play with this a little bit, this kind of gives you a better idea how this stuff all links together. But again, that's just me because Chemistry for Funeral Service is the book that I used when I was in mortuary school. So, aliphatics, or chains. Okay, chains can be divided on the type of bonds that are present. Single bond, double bond, triple bond, or it might be a side chain. Okay? When you sit down to study, as soon as you sit down to study chemistry, write the stuff on your scrap paper. You just do it. Do it and throw it away. Don't need to look at it again. You're bored at the funeral home? Write it on a note card, throw it away. You're on your phone, you got a little doodle app, write it out, delete it. Just repetition, repetition, repetition. Chemistry is one of these subjects, folks, that unless you work at it, you're simply not going to get good at it and you're not going to understand it. You cannot fake your way through chemistry. I don't know anyone that has ever faked their way through chemistry. Some of you full-time chemists might know someone because you wonder how the hell it is they got their degree. But overall, chemists actually have to be able to do the work. The alkanes are acyclic hydrocarbons, are chains. Chains, in which all of the carbon-to-carbon bonds are single bonds. They're all dashes. You can either have a dash, you can have an equal sign, you can have a triple equal sign. But in single bonds, that's what you're looking at. That's what ANE means. Single bond. Which is why 1,2,3YL, ANE, ENE, YNE, sidechain. Alkanes are considered to be saturated because they won't hold anything more. So, review. Carbon has 4 electrons it can share. It can create up to 4 bonds. And here we have methane. Single carbon with 4 hydrogens, right? Can't do anything more to this. If we did something like this, we could add something else, right? But right now, all this is full up. This is saturated. That's all saturated means is it meets the 4. That's all there is to it. We're done with it. The prefix alk, ALK, refers to chain. Refers to chain. And the suffix ANE equals 1. Single bonds. Single bonds. Literally means chain of single bonds. Boom, that's it. The name tells you what it is. And the characteristic type of reaction, what this thing wants to do in the wild, is it wants to replace, because it's already pretty stable. You've got these 4 hydrogens floating around. There's nothing to break down. All you can do is toss a hydrogen and bring something else on there. Nitrogen, maybe bromine, whatever. We'll talk more about bromine when we get to the alkyl halides. Spoiler alert. That's all substitution or replacement means. Some people want to try to think that this is heavy-duty science stuff. No, it just means that with this hydrogen here, we got to toss it and bring something else in, because this is pretty much already a fairly doesn't want to do anything more type of situation. It has 2 AKAs. The first is the paraffin series. Well, this is the one you're going to have to memorize. Bad news, man. Okay? Bad news. The second, and this is going to be the same for all the hydrocarbons, whichever the first one in the series is, the very first molecule we have, that's going to be the name of the series. So in this case, the first molecule we have that's a single bond is our friend methane. So it's known as the methane series. And they have the general molecular formula of CnH2n plus 2. N equals number. That's it. People are like, oh my God, it's the end of the world. I have second grade mathematics to worry about. If I wrote that like that, it wouldn't be too much of an issue because you're used to seeing X. And that's exactly what we're doing here. So if we have 22 carbons, the math is simple. 2 times 22 plus 2. You're going to name it? You're not going to name it because no one's going to know how to name 20 plus stuff. Like, it's super simple once you learn how to name stuff that high up. It's kind of like numbers in German. But that's all the math is. So if someone said, well, how many hydrogens are attached? 46. What if you had 30? 2 times 30, 60, plus 2, 62. You're not a genius. The math is just simply that easy. Honestly, that's all what the general molecular formula is. And remember, you now have general moleculars. You have a regular molecular formula, which is whatever it's actually supposed to be. This is how you determine the molecular formula. You then have the structural formula. So if we want to draw methane, this is what methane looks like in structural form. This is what it looks like in molecular form. And just so happens to be that this is what it looks like in a line formula. It's the same. It's the same. This is easier to demonstrate on something like ethane, right? Because here's ethane. Let's draw all this out. And again, this is how you master. Okay, this is the structural formula. Now I'm going to do the molecular formula, which is C2. What's 2 times 2? 4 plus 2, 6. C2, H6. 1, 2, 3, 4, 5, 6. That's looking right so far. And what's the line formula? CH3, CH3. Line formula, molecular formula. One tells you what's in there and how much. One tells you in a single line what it's supposed to look like. One tells you in like 2D what it's supposed to look like. That's what these formulas do. Don't let the fact it's science drive you nuts. Don't, okay? The book then goes into the math. I just showed you. Doesn't matter how big or how small the number is. Simply put the number in for n, run the math, and you'll be fine. So now here's the naming stuff. This is what drives people nuts. This drives me nuts. First, no matter what, name the longest chain of carbons. Step 1, count the C's. Literally, count the C's. Then, count the side chains. Okay? You're going to go through looking at a molecule and you're just going to be like, okay, this one has 7, this one has 2, this one has 4. That's the first thing you do. You'll then give addresses. More on that coming up. The name is always written from right to left, but it is read left to right. As we fill out the names, we're going to start here and then work our way in this direction. But when we say it out loud, we're going to start over here and go in that direction. So, without putting numbers or any identifiers up, if I started with a base chain of 8, we'll talk about this in a second. All single bonds, we're looking at octane. Now, what if I had 3 side chains on there? One with 2, one with 4, and one with 7. Well, that's eth, that's bute, that's hept. Side chain is YL. How do we know that? Because we've been writing side chain YNE, ENE. I'm used to writing it top to bottom. ANE. So, if we were writing this out, octane, ethyl, butyl, heptyl. But when we say it, heptyl, butyl, ethyl, octane. And there would be numbers here telling us where these things go. We'll get to that in a second. But people have trouble with this. Oh, it's written from left to right, or it's written from right to left, it's read left to right. That's all we're saying, is we start on this side with the largest, the base chain, and then we start adding the side chains. But when we say the word, we start over here and we go in this direction. The longest chain gets ANE, remember, base chain. Everyone else, side chain. Now comes the most important thing. I'm doing it again. This is how you learn it. This is how you master this. Okay? If this is what your professor wants you to do. Because the truth is, probably most professors who teach this aren't chemists, and they don't have a good grasp of this themselves, so they're not going to want to ask a lot of questions on things that they don't understand. And because you can't draw out lots of pictures, you're not going to get a single picture on your board exam, whatever you do has to be in written form. And there are some very, we can use line formulas. We can absolutely put a line formula on the screen and say, what is this? And you'd have to figure it out. The next thing you're going to do over here, again, if you have to master this, but this is how you do it. And this is where people mess up. You try to memorize this. And the way you memorize this is you think of this as a new language. If I was to ask you to count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Come on, press a fin. Okay, well, I'll do it in Spanish. I can't count to 10 in Spanish. 1, 2, 3, 4, 5. I can do it up to 5. Okay, then I think it's 6 is next, and I can't remember what 7 is. German, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can do 10 in that. French, 1, 2, 3, 4, 5. Can't remember what 6 is. Japanese, 1 to 2. Each, ni. I don't know any Portuguese. Can't remember the numbers in Latin. Sorry, boy choir folks. So now you have to learn how to count to 10 in chemistry. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. You have to learn to count to 10 in chemistry. And that's how you practice it. Every time you sit down to study your chemistry, if this is something important for your professor, you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. Other side, ein, ein. Why? Because prefix, suffix. This plus this gives you what you need to know. This gives you what you need to know. So you have to memorize how to count 1 through 10. So the book throws at you, name the alkane of 1 carbon. What's 1? Meth, ane. 7. Hept is 7. Single bond, ane. Double bond, hept, ene. Triple bond, hept, ine. Side chain, hep, til. That's it. Single bond, 1, 2, 3, 4, 5, 6, 7. Heptane, heptene, 1, 2, 3, 4, 5, 6, 7. For the sake of argument, we'll put it right on 1 so it can't be confused. Heptene, 1, 2, 3, 4, 5, 6, 7. And then a side chain would look just like this, except attached to something greater, which means you literally have to draw 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Because remember the rules for naming. Find the largest chain. Start with that. Oct. Right? Find the largest chain. Determine single bond, double bond, triple bond. These are all single bonds. A and E. How do we know that? Because we wrote them on our scrap paper right as we started. And then the next one over here is 7. What's 7? Hept. Why do we know? Because we wrote it over here. It's a side chain because that's the suffix for side chain. And then we have to determine what number it falls on. Well, it's on the first one. 1-heptyloctane. That's it. I didn't prepare for this. I just wrote that down as a demonstration, and there it is. This is how you practice it. Get with a friend. Take a note card. Take a bunch of note cards. Write 1 through 10. Have them drop down 2 or 3 cards. Then put the ane, and then have a bunch of YLs. The largest number gets the ane, the ene, the ine, whichever one with the biggest bond. And then the side chains, all the smaller numbers, get the side chains. And now draw that out. Draw that out. Make up some numbers, and we'll get into how we put numbers on there and how we can play with this and how we can double check it coming up. But you just play with it. You literally just play with it, and eventually it will stick. I found when I started playing like this, it clicked very, very quickly for me. And I know that there are people out there say, hey, this isn't necessary to know. But when you start playing with this, it helps reinforce some of the rules and some of the other things. So it says, name the alkane of 2 carbons. Well, if you have the prefixes there and the suffixes here, you look at 2, eth, ane. Professor Finn, what if it's a closed chain? Guess what? Can't have a closed chain yet. We don't have enough. Right? We have to be able to tie the 2 together, and we can't do that with 2. We can't do it with 1. You're going to see that when we get to the aromatics. So the book gives you this. Okay? The book gives you this as a demonstration. It walks you through it. So let's run the rules. Okay, let's run the rules. First is find your largest. There's your largest. Notice I drew the box around it. Why? Because later on when I'm drawing a box over here for the side chain, I don't want to inadvertently do something like that. If I do that, that creates a problem. So, by drawing the boxes, guess what? I can't confuse what I've already counted and what I haven't. If you're doing this digitally and you want to be cool kid, impress your professor, some of you like to use colors, then by all means, use different colors to mean different things. So, 1, 2, 3, YL, ANE, ENE, YNE, and side chain. And on this side, we'd have 1 through 10. I don't want to write that all out just so I don't have like an 1.5 hour long video. So let's count. 1, 2, 3, 4, 5, 6. We have 6 carbons. What's the word for 6? Hex. Right? That's the prefix for 6. Hex. We have all single bonds. Ane. Hexane. So what I'm going to do is I'm going to write the red box in red, the name in red to match up. Now, we look at the side chain. It's a single carbon, one carbon. What's the word for one? Meth. Here in Florida, we know all about meth. And what do we have? This is a side chain. Methyl. So right now we know we're dealing with methylhexane. A hexane base molecule. Okay, a hexane base molecule with a side chain of a single carbon methyl. Methylhexane. What's the next thing we have to do? We have to determine what's the proper place for the side chain. And your book says you have to do it with smallest numbers. And what you do is this: 1, 2, 3, 4, 5, 6. In this case, and folks, when you start off, this is what you do every single time. There's no shortcuts here. Yeah, I know later on you can just look at this and see it's a 2, you're good. But this is how you start off. And especially when things get more complicated, this is how you need to do things. This is 2. 2-methylhexane. I'm sorry, 2-methylhexane. Might have just said that unclearly. So then the slides take you through the process. And I'm going to leave the original one up there because I just read this through bit by bit. I might delete it just to delete it. Right? There's 1, 2, 1, 2, 3, 4, 5. And that's how we determine what the smallest number is. And this gets dangerous. Okay, this gets dangerous. Because, in fact, you know what I'm going to do? I'm going to get rid of this. And we're going to use this color for this side. Okay? So, the issue becomes, because what if we had something like, let's get rid of this. You know what? That's a problem. Whoopsie, I didn't want to do that. Don't want to make this too terribly confusing. So, let's put right here. We'll get rid of that. And we're going to drop another one of these bad boys right here. Okay? And just so we can differentiate it, because I don't want to get into... What if I wanted to put that right there? We'll name this in a second just to say we've named it. Okay? Promise. In fact, you know what? Just because. Just because. Why not? Make it a 3. When we look at lowest numbers, we determine this first chain is on a 2, right? What this means now is that anything we look at, we are now going to count from left to right. We're going to count from left to right for everything. We are never going to count, in this case, from right to left. Show you why in a second. Okay? So first things first. Whoopsies, get this up here. Let's redraw this on the whiteboard. So we had... I already can't remember. What do we have? 1, 2, 3, 4, 5, 6. Okay. So we had 6. Do 1, 2, 3, 4, 5, and 6. Here we had this. And then 1, 2, 3. I am going to omit all the hydrogens. I'm just going to be honest. I don't feel like drawing those all out. Again, reduce time. Okay? So we had 1, 2. Okay? If I am going to work the system, there's my box. There's my second box. Here's my third box. I have 6 here. I have 1 here. I have 3 here. Again, we're going to name this. Okay? Promise you we're going to name this. We're not going to count from this direction. 1, 2, 3, 4, 5. But I'm going to leave it there to show you how this messes people up and how it breaks things and how you can check yourself so that you don't fall into the trap. What does the rule say? First thing you're going to do, you're going to write it from right to left. What's the largest one? We have 6. That's hex. That's not going to change. We know that because we have hex on the left, single bonds on the right. We're looking at hexane. Next up, we have a 1. That's going to be meth. It's a side chain, so it's methyl. And then we have a 3, propyl. And with all my stuff written down here on my scratch paper while I'm practicing, I can't possibly screw this up by, does bute mean 3 or does it mean 4? And I do that all the time when I don't write the stuff down. I always confuse PROP and BUT for 3s and 4s. I do it all the time. Senior moments. So now I have to tell in my name where these things are. So using what we're supposed to here, left to right, because that's the way we determined our smallest number for the first one. Methyl is on 2. 3, 4 is on the next one. So we are looking at 4 propyl, 2 methyl, hexane. 4 propyl, 2 methyl, hexane. So what would happen? Okay, what would happen if, and people do this all the time, we use smallest numbers for everything. We don't worry about lefts or rights. We just use smallest numbers because we use smallest numbers. Well, let's look. Okay? So, the methyl doesn't change. The methyl doesn't change because going on one side it's 2, going on the other side it's going to be 5. Can't change it. 3, 4. Right? Because remember, up here it's 4 propyl. Lowest number here is 3. Lowest number here is 3. How do we check? Are these things equal? We draw it out. So let's do this in green. 1, 2, 3, 4, 5, 6. So far, so good. 6 is 6. 2 methyl. Okay, so there's my 1. So far, so good. 3 propyl. 1, 2, 3. Cool. What's our problem? You see it? In number 1, you have a carbon between this one and this one. You have literally a space between these two. On number 2, they're side by side. These are not the same molecule. This is why, once you determine a direction, you have to use that direction for everything so that you can keep this in the proper orientation. A lot of people make the mistake of just using smallest numbers, and they end up with things that are wrong. Okay? So I'm going to erase this because we're probably going to need this later when we do some more stuff. Go a little bit crazy. All right, you know what? We're just going to do it this way because I can. Haha. I don't know why I'm in the habit of not using the pen for erasing on the whiteboard. This is why the lefts to the rights matter, okay? This is why the left to the rights matter. If we go back to this one, straight up, not doing anything funky to it, this comparatively should be easier. 1, 2, 3, 4, 5, 6. We already know this is hexane. We know this is a methyl. And it's on 2. So we should be looking at 2-methylhexane. And that's exactly what we're looking at, 2-methylhexane. Deep breath. Alkenes, double bonds, right? We had 1, 2, 3, and YL. This is single bond. This is double bond. This is triple bond. I don't know why I just wrote all that down there. ANE, ENE, YNE. So now we're looking at double bonds, equal signs. Shouldn't do that. Should do that. These are considered to be unsaturated. So real quick, let's look at this. If I did this, here's our friend ethane. We know the alkanes are saturated. They're only going to work by replacement or substitution. They're going to take one of those hydrogens, we're going to toss them, move on with our lives. Now, we're looking at ethene, an alkene, double bonds in the middle. So now, we can do one of two things. Okay, now we can do one of two things, as I put these people on mute. We can either replace one of these bad boys, which we're not going to do, because as a class, they don't want to do that. That's just their nature. Instead, what they're going to want to do is they're going to break that double bond. They're going to want to break that double bond so that they can add more things here. So they are considered unsaturated. And their preferred reaction is addition. Break the double bond so you can add more stuff. And then when you've added more stuff, you become an alkane, and now all you can do is substitute. Spoiler alert, alkynes are the same exact way. They're going to want to take this triple bond, break it, they're unsaturated, so they can continue to add things until they get to an alkane, and then they're going to settle down. There are 1,000 different ways that a chemist can explain this better than I. But since all I do is coloring book chemistry, this is how I'm going to explain it to you. As simple as I can. So alkenes are going to want to add. They're going to want to take that double bond, break it, and try to turn themselves back into an alkane. There are several names. Olefins, that's the one you memorize, or the ethene series. So remember, ane, ene, and ine, ane, ene, and ine, all refer to the type of bonds between carbons. You cannot have a double bond between carbon and no other carbon and have it be an alkene. So methene does not exist. Okay? Methene does not exist. Ethene does. As a result, it's the first in the series. So take a moment. We know that triple bonds are coming up. What do you think one of the names for alkynes are? The ethyne series. The ethyne series. The smallest molecule is what is going to name the series or be one of the names for that series. Let's step away from this for a second. Just for later on. Just to prime this for later on. We've been talking about aliphatic, right? Chains. So what happens when we go to aromatics? Do we have a closed chain with one? Nope. What about two? We got a line. Nope. But three, we can finally close the chain and link them all together. What do you think the smallest of the aromatics is? Well, what's 3? Prop, single bonds, ane, aromatics, cyclo. Cyclopropane. Cyclopropane. We haven't even gotten that far, and already we can just kind of look at it, put the words that we have studied together, and come up with an answer. We'll see more about them a little bit later. So alkenes. General molecular formula, CnH2n. Oh my God, more math. Okay. Right? Here's our friend, ethane. And we know its molecular formula is C2H6. Why? Because if we substitute 2 and 2 here, we get 2 times 2 is 4, plus 2 is 6. Now, we have this. Look at this. CN2N. How many do we have? 2. How many do we have? 4. We went from +2 to neutral. And then we can count. 1, 2, 3, 4. 4. We're good. Spoiler alert. What do you think happens when we do triple bonds? Remember, we can only have a total of 4 connections. There are 3 going carbon to carbon. This hasn't changed at all. The CN hasn't changed at all. The H, 2N, hasn't changed at all. It's been there no matter what. So, how do we get to only 2 H's? 2 times 2 is 4, right? 2 times 2 is 4. So from 4, how do we get to 2? We subtract 2. So generally speaking, if we had 22 carbons, looking at an alkyne, 44, right? 2 times 22 is 44, minus 2, 20. Using the general molecular formulas, you can determine very quickly, very, very quickly, how many of these things should be there. That's where this comes in. Don't let the math scare you. This is simple second-grade arithmetic. You're solving for x. And when you see the same number goes in both places. What's the good news on all the ALKs? CN, H2N remains. All you have to remember is which one adds, which one subtracts, and which one doesn't even play with it. And it's not hard. If you're in a pinch and you can't remember which one does what, do yourself a favor. Just count it. And if you remember this, if this is all you remember, see? And how do I get to 4? 2n plus what gives me 4? 2. And you're good. Realistically, the best way to do it is with ethane, because of the fact that you can't process enes and ines with one molecule. But this is how you can double check it. This is how you can double check it. And if you get these computational problems, especially on a professor exam where everything's worth the same, you pass right by it, you come back, and you finish this last. Anything you have to compute, you compute it last. They're all worth 2 points. The only time you worry about getting this done is if this is worth 5 points, everything else is worth 1. Then you prioritize it. You want to make sure you have space for it. But even then, chances are pretty good you'll get through the rest of the exam, finish all the other questions, and then go back and do your 2 or 3 computational questions. Deep breath. There are rules for the alkenes just like there's alkynes, or for the alkanes. First rule is the same. When in doubt, go with the largest number first, because that's the rule, same as the previous. Then you're going to focus on where the bond is. It's not about smallest numbers with the side chains anymore. It's about where is the smallest number for the bond. Remember we talked about right to lefts, lefts to right mattering? You're going to determine that right to left, left to right using the bond. We'll see this in a second. How you name it? Same exact thing. You name the largest, and then you name all the side chains. Then you're going to put a number where the bond is, and all the other numbers for all the side chains. Now, the book gives you this. The address of the carbon next to the bond, which has the smallest numbered address, is the address of the double bond. So if it's between 3 and 4, then the address would be 3. Let's get to an example, show you how the book wants you to do it, and let me show you something a little bit simpler. At least what I think is what is simpler. We've already talked about side chains. Nothing changes with how we write it versus how we say it. We are always identifying by the number of carbons in the chains because that's the number that matters. And side chains all get YLs. So, let's take a look at this one right here. Okay? Let's take a look at this one right here. And I don't want to put text on here. 1, 2, 3, 4, 5, 6 with, okay. All right. 1, 2, 3, 4, 5, 6. And it dropped a carbon, I think, right here. Just double check. Yeah, it's on the second one. Cool. All right. Again, I'm not going to put all the hydrogens. I'm just going to save that time. Your book says what it wants you to do. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Block this off. Take a look. What's the smallest one? 3 and 2. What's the smallest number? 2. That's the number we use. Perfectly acceptable way of doing this. Absolutely fine. Absolutely fine. My way of doing it. I just number the bonds. I just number the bonds. And you're going to do this for both alkenes and alkynes. This is the same for both. The rules don't change. They're all the same. So why do we start with the bonds? Because the bond is the most important, and that's going to tell us right to left, left to right for counting our carbons. So we now know, hell or high water, we're going to be counting this way. 1, 2, 3, 4, 5, 6. Because the bond tells us that's the way we have to count to keep the smallest number for the bond. So let's look at this. Okay, let's look at this. First things first. 1, 2, 3, 4, 5, 6. What's the number for 6? Hex. Okay, hex. Remember, we're going to write this from right to left. We're going to say its name from left to right. We have a double bond, which makes this hexene, E-N-E. And we've already identified this is on the second bond. Period. Done. Good. We have a side chain, methyl, which is on number 5. So we are looking at, in this chemical instance, 5-methyl-2-hexene. Then people make the mistake. They start counting the carbons. Oh, this is on 2. This is on 2. So this is actually 2-methyl, and this is wrong, 2-methyl-2-hexene. Okay? Let's draw these out. Remember, this is in a reverse orientation, so when you write these out, you're going to write them out like you see here. So let's write both of these out, and we know that this one is correct, this one is wrong. So what do these look like? Well, Let's do this one is number 2, this one is number 1. 2-hexene. 1, 2, 3, 4, 5, and 6. Here's number 2. 1, 2, 3, 4, 5, 6. Try to make this as similar as possible, right? We know the double bond is on 2. We're good. Okay, we're good. Now, look where we drop the carbons. On the right one, 1, 2, 3, 4, 5, it goes here. On this one, it goes here. And if we look at the original, 1, 2, 3, 4, okay, we look at the original. Look at where the double bond is versus the carbon. Look at where the double bond is versus the carbon in the wrong one. They're right on top of each other. Why? Because we use shortest numbers for everything. Once we determine which way we need to count for the bonds, we have to use that thing for everything else. And in this case, we have a huge space there, and we have a huge space here when written in normal orientation. All we're doing here is, if you look at the bottom left, you'll see my Altoids, okay? When we first saw this, the way it was presented in the book, it looked like, well, it was backwards, okay? So the lid is over here. In this case, when we write it, we always put the lid on the right side. We always put it in one direction. So we have to put the orientations like this, and when we do that, we notice the gaps, right? We notice there's a gap between these two. There's a gap between these two. These are likely correct. If they're on top of each other, there's no way that's right, because that's not what we were presented originally. We take this away. Look at the gap. We have 1, 2, 3 carbons. 1, 2, 3 carbons between the bond and the side chain. And the one we just drew, 1, 2, 3, 4, 5, 6, we had the thing side by side, no gap at all. No gap at all. So then we go through, we're going to see that this is 5-methyl-2-hexene, right? 1, 2. And because we're counting in this direction, 1, 2, 3, 4, 5, there it is. There it is. Deep breath. Alkynes. Alkynes. How do you know it's an alkyne? It's got a triple bond. That's it. Also known as the acetylene series. And we already talked about the smallest one always gets the name. Ethyne. Always. Okay? The molecular formula, already talked about this. In order to get what we see here, right? C2H2N, which is going to be 2 times 2, is 4. How do we get to 2? We have to subtract. This is how we can double check it. And this will always give us C2H2. Now, there is no difference in how we name between the double bonds and the triple bonds. They're identical. They're identical. And you will never be presented with an example that has double and triple in there. Plain and simple. It's just not going to happen. Okay, it's not going to happen. So real quick, let's do something that is so completely ridiculous that you will never see it in school. Something so incredibly broken that you will never see it in school. And likely I'm going to screw it up and someone's going to point it out. And when that happens, feel free to go ahead and share it with others, show people how stupid I am. Okay? So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 1, 2, 3, 1, 2, 3, 4. 2 and 1, because why not? And let's, for the giggles of it, put a triple bond right there, just to make our life miserable. Oh my God, Professor Finn, this is going to be awful. You're right, it's going to be awful. What's the first thing you do? Exactly as I told you, box it off. And then, be smarter than the professor and give yourself more space. Okay, put a 2 right there. We haven't talked about one of these things yet. Then, why am I doing this? So I don't miss one. And I don't recount a carbon. 2, 2, 4, 1, 3. Now I got something interesting. I got 2 groups of 2. Don't panic. Don't panic. What's the rule say? You start with the largest one. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is non. Triple bond, get a triple bond right here. There should be a triple bond because I covered over it with the box. Non-9. We're going to need a number here. I'm going to need a number there in a second. Then what do we have? We have a 1. 1 is meth. Side chain, methyl. We have 2 of the 2 carbon side chains. Ethyl. Another way we could write this. Diethyl, because that tells us immediately we have 2 of these. No ifs, ands, or buts. We have a 3, propyl. And we have a 4, butyl. Now comes the fun part. Oh my God, where are all these numbers? Deep breath. Count the bonds. 1, 2, 3. We already know if we have a chain of 9, 3 is going to be the smallest number because counting the other way is going to give us something larger. So we already know this is 3 nonyl. Or 3 nonine, I'm sorry. 3 nonine. And now what else do we know that's very important? We got that number going left to right. That means we have to count everything else from left to right. Which, if we haven't already, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I just count the numbers. So where's my methyl? My methyl is literally on 9. My 2 ethyls are on 2, and they are on, that's 8. My 3 is on 4, and my 4 is on 6. I am looking at 6 butyl, 4 propyl, 8 diethyl, 9 methyl, 3 nonine. Professor Finn, it can't be this simple. It literally is this simple. If you just do this a couple hundred times. Draw something stupid out and name it. Then draw it back. Did you get it right? Well, my professor makes me do this in line formulas. Oh, really? I'm glad you brought that up. Because remember, we're missing all the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Starting on the first one, CH3, because there's going to be 3 hydrogens. That one's done. Next one has CH, followed by CH2, followed by CH3. Right? This is going to have a single hydrogen coming off the bottom, and then we're up on the chain. Followed by, this one's done. Another carbon with nothing attached to it because the one attachment it would have, it's connecting with the carbon. So, triple bond attached to a carbon, which in this case I've created a chemically unstable thing because it looks like, let's see. 1, 2. Yeah, I missed a hydrogen there. This looks, let's see. Yeah, that looks like it's stuck. That's good. Problem is this couldn't exist when running the math chemically because neither of these could share an electron. But I didn't do this with the idea of keeping this like scientifically plausible. I just did this for naming purposes. So if I was going to do this, there's my triple bond followed by, in this case, CH2, CH2, and then a CH3. I mean, this thing's going to go on forever. But you get the idea. I can then practice writing this in line formula. And what did I do? I sectioned all these off. So as I finish something off, guess what? I can cross it out and I can move on to the next thing. And every time I finish something, I am able to finish it off. This stuff will literally teach itself if you put in the practice. So deep breath. Deep breath. Again, you want to run these things? By all means. By all means. Hit me up with a Friday with Finn and we can do some of that. Aromatics. Aromatic hydrocarbons are exactly as the name sounds. We are attaching all the carbons together so that they link up. These are called cyclic, closed chain, or aromatic. That's all that means. That's all that means. There's other reasons why we use the word aromatic later, but for right now, don't worry about that. Don't think about that. Aromatic means circle. Specifically, we're going to look at the cyclanes or the cycloalkanes. These things, cyclane, are equal to each other. 1 and 2 are equal, okay? And their only difference is they form rings. They connect together. That's it. We're not going to ask you to go crazy naming these things, except for if I ask you, hey, what's a 8-ring circle of carbons called? Oct, 8, ane, single bonds, circle, cyclooctane. That's it. But notice we don't have a 1 and 2, remember? 1 can't form a circle. 2 can't form a circle. It's not until 3 that we can finally form a circle. And if you ever see a chemistry drawing or something and you see deet, all that is a carbon chain, a bunch of carbons connected to a closed chain at the end. That's all this stuff is so if you can draw it out so you can look at it quick and you can see exactly what it is you're getting into and where certain things are. Fun part, the cycloalkanes are equal to the same formula for alkenes in computing how many carbons and hydrogens. And again, if you need to figure this out, wait till you get to the end. How quick did this take me? 10 seconds? Not even? Right? Now I can double check it. 1, 2, 3, 4. That means this makes 4 connections. I'm good, so I know this is right. And 1, 2, 3 carbons, C3, and then how many of my hydrogens? 1, 2, 3, 4, 5, 6. 2 times 3. How do I get 6? Because the CH2N doesn't change for anything. If I simply draw one out, I can figure out what the formula is. Cyclopropane is the smallest. The book then talks about cyclo referring to the ring structure, and then prop refers to 3, ANE refers to single bonds. I've already kind of demonstrated that. And then you start going up in numbers. Cyclobutane, cyclopentane, cyclohexane, cycloheptane, cyclooctane, cyclononane, cyclodecane. What's the one we care about? Benzene. The one we care about is benzene. Benzene okay? Benzene has these double bonds. And you might remember that when we're looking at single bond stuff, only thing we could do is we could take hydrogens, right? We could take the hydrogens and we could replace them because an alkane is saturated. All 4 bonds are being used. Life is good. When you get to the double bonded stuff, when you get to the double bonded stuff, double and triple bonds will have a tendency to want to break this so we can go back to adding more stuff to it. Addition, right? So here's the crazy thing. You have all these double bonds, and yet, first thing is the double bonds don't actually happen this way, but also this molecule doesn't want to break these double bonds, not by any stretch of the imagination. It wants to stay this. It wants to stay just like this. And what it will do instead is it will want to drop one of these hydrogens and replace it with anything else. Benzene wants to stay a benzene ring and just modify its attachments. It doesn't want to cease being benzene. Whereas any of the alkenes, any of the alkynes, they want to cease being alkenes and alkynes, and they want to become alkanes again. So something funky about these double bonds is something called resonance. Something called resonance. These double bonds aren't actually here. These double bonds vibrate between all the carbons. And what it does is that vibration makes it extremely stable. This is called resonance. This is called resonance. It's the resonance that wants to keep benzene benzene and would rather substitute a hydrogen than mess with the benzene ring. And again, I'm not expecting you to learn this from a chemist standpoint. There are better ways to probably explain it in a true chemical fashion. But for understanding what this thing is doing, that's the best way I can say it. Okay? And here's where the book tells you that it just acts like an unsaturated, or it acts like a saturated compound and not an unsaturated. Because it wants to get rid of a hydrogen, add something to it, rather than break the double bonds. It doesn't want to do that. And the majority of the aromatic compounds, the majority of the cyclical hydrocarbons, the alkenes, run by replacement. They want to dump the hydrogens. They don't want to change their core molecule. Deep breath. Alkyl halides. First thing you have to work with the alkyl halides is you have to go back and you have to remember your halogens. Okay? Because you have to be able to identify the halogen, because that's going to make a big difference here. The general formula for these guys is R-X. And how do you know that? Because it's right in the name. You're going to have your hydrocarbon on one side, followed by the name of the halogen. There's two ways we can name things. Okay, there's two ways we can name things. The naming conventions, just think, I don't know anyone that's going to ask you one of these questions, okay, if we're going to be honest, but the naming conventions follow anything. Pretend that the halide is like a side chain when it comes to putting the number where this thing should be. So if it's on 1, you probably don't have to list it because it's assumed to be on 1. On this one, it could either be on 2 or it could be on 3, so you're going to have to list it as 2 because that's the smallest number, right? 1, 2, 1, 2, 3. You go with the smallest number. That's going to be 2. If we wanted to name these, just to say that we did, what do we have here? 1, 2, 3, 4. Single bonds. We don't see anything more than single bonds over here. Okay? So what's the number for 4? It is Bute. What single bond suffix? Ane, A-N-E. Butane. So we're dealing with butane, but then we have bromine sitting right there on the end. We're going to see there's two ways we can name this. This is the first way. Bromobutane, where we name the hydrocarbon, okay? And then we just put something ending in O that matches whatever the halogen is. Fluoro, iodo, chloro, bromo, depending on which one of these. So in this case, bromobutane. Or we can name it just like the class, alkyl halide, where we treat this as a side chain for naming purposes. And then use the halogen. What do I mean by this? What's the halogen? In this case, it's bromine. Right? That's the halide. Then, what's my hydrocarbon? Bute. Bute. And what's the suffix we use? It's right in the name, YL. So we are dealing with butyl bromine. Both of these are equal. They both mean the same exact thing. Bromobutane and butyl bromine are the same exact thing. So what's the difference between A and B? They're both 4. They're both 4. But the bromine is now on this carbon. 1, 2, 3, 1, 2. 2 bromobutane. And I can't remember if it's butyl 2 bromine. I think it is. I'm just going to go with that because I don't feel like looking it up right now, if I'm going to be honest. And then we have this hot mess right here. Oh my God, Professor Finn, we're never going to be able to name that. I got to be honest. I don't remember how to name it. I don't remember what the name actually is. But I'm okay going on the internet and look like an idiot. I've done it more than once. I will likely continue to do that until the day I die. And even then, if God has mercy on me, he'll make me look like a fool on my dying day, because that would just be an absolute complete circle, and I would be delighted. So, look at me go. Step 1, what's the largest chain? 3. What's the word for 3? Prop. Do I have any double or single bonds? Triple bonds? Single bonds. I'm dealing with propane. What do I have? I got a bromine. This is probably going to be easier for me to put that there instead of something else. So let's just start with that. Where's it on? No matter what, it's on 2. I have to put 2 because the other place it could be is 1. I can't confuse it. And it would be confusing if I left it off. So 2 bromopropane. And then what do I have? Methyl on 2 as well. 2-methyl 2-bromopropane. And I suppose if we're going to name this using the YL method, which I don't know if is appropriate or not, we would have 2-propyl. I'm sorry. Nope. I suppose naming convention-wise, propyl 2-methyl 2-bromine, I guess might be the name of this. Again, I don't know. I didn't look it up, and I don't feel like trying to figure it out, like jumping on the internet. And no one is ever going to ask you to do that. The moral of this story, folks, is that if you understand the naming conventions and you practice this, you can look at that and not get scared by it. I'm honestly not scared if I'm getting it wrong. But from a logic standpoint, do I have my 3? Yes. Propane. It's easier for me just to call it bromopropane because that just, I think, rolls off the tongue better. Where is it? It's on 2. And then where's my side chain? On the second carbon as well. What is it? Methyl. 2-methyl 2-bromopropane. If I'm right, great. If I'm wrong, awesome. The internet will tell me. You should never have to do this in real life. for funeral service purposes. Again, demonstration only. The general class is R-X. The alkyl is the R, this is the X. It's a placeholder. We're going to see lots and lots of R's and OH's going into the next thing. Like if we do this, we're looking at an alcohol. We do this, we're looking at an amine. We do this, we're looking at carboxylic acid. The R is always the hydrocarbon, and whatever this is whatever it is. Professor Finn, why is it an X? Easy. As an alcohol, we know a hydroxyl group is important. More on hydroxyls next chapter. We know as an amine group is important. What's our problem? Chlorine, bromine, iodine, and fluorine. It can stand for any one of them, so we can't use just one of those. We have to have something that represents all four. What's an easy one? X. X equals whatever it has to be. Don't overthink it. That's all it means. If you have 4 halogens, the X has to represent either of those 4. That's it. And as for naming purposes, we just ran one. There is nothing different. We treat it like a side chain. That's it. That's it. So it gives you 2-chloropropane. 2-chloropropane. And it gives you a line formula. It's kind of like a structural formula, right? So you'd have these 3 right here. You would have this bad boy right there. And then you would have that right here. 2-chloropropane. And again, I would love to know, I'm probably going to look it up after this because I'm just going to be curious, how we would name this with, actually, it would probably just be propyl 2-chlorine. Propyl 2-chlorine, if I'm thinking about it. The simplest of the alkyl halides is going to come off of methane no matter what it is. Because it's an alkane. We can have methane attached to whatever. So in this case, it gives you chloromethane. And now, this brings up this uncomfortable thing. And that's what the next slides are going to be. If we have this, we have chloromethane. If we have this, now we have 2 chlorines. We have dichloromethane. That tells us there's 2 there. So guess what happens when you have 3? Trichloro, and finally the last one, tetrachloromethane, carbon tet, which tells you have 4 chlorines. Hardest one to remember there is tetra. And then even then, think of the game Tetris. How do you form a Tetris? By using a tetrad, the 4 block, to finish 4 lines at once. Tetrad, 4. Okay? Then it goes through whatever. So remember R-X? What if I wrote this? Name this. This is supposed to be an H. Let's make sure that looks like an H. Okay, that's an H. Well, we have carbon. Trifluoride. Or we have trifluoromethane. How do I practice it? Exactly as I did. And I do this for fluorine, I do it with iodine, I do it with chlorine, and I do it with bromine. That's it. That's how I practice it. R is the meth. The X is the fluorine. Methyl fluorine. Alkyl halide. I really wish I would have figured this out when I was in mortuary school because I would have had so much of a better time in chemistry. What's the fun part about carbon tet? Back in the day, it was used in fire extinguishers. What's the bad thing? If you inhale the fumes, it kills you. So we try to find other fire-suffocating things that don't kill us in the process. And it's not like formaldehyde. We just spray a little bit of ammonia in there, and all of a sudden, it takes care of itself. So, folks, 1 hour 20 minutes. Hour, 20 minutes. Thanks for sticking around that long. I don't want you to waste a lot of time on this stuff if your professor's not going to put you through it. But if you want to see how this stuff works and how it relates, and I think drawing these things out helped me a lot when I started learning about the alcohols and all the rest of the stuff going into the next part of the book, that made a lot more sense once I mastered this. And then what you have to do is start with what I told you. On this side, side chain, ane, een, and ein. On this side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. On every piece of scratch paper, practice it when you're bored until you can literally drop it like I just did. And then from there, all you have to do is remember the rules. And the best way to remember the rules, draw something out, put something stupid on there, and then start messing with it. Make it a double bond, make it a triple bond, move it somewhere else. And if you have questions, above all else, if your professor understands this, say, hey, is this right? Am I doing this right? Hopefully, they have a grasp of this. And I'm going to be the first one to say, just because your professor doesn't have a grasp on this does not mean they're bad professors. Okay? Chemistry is one of those things that just dogs people in mortuary school. That's the truth. And usually the low man on the totem pole gets stuck teaching chemistry and they don't like it because they don't understand it. And that was me 5 years ago. Now, I love teaching this stuff. I love it because I see how it works, I see how it interacts with each other, and I've grabbed a mastery of it. So folks, Professor Finn signing off. Hope everyone had a fabulous day today, and I will see you next video.